we just finished the counting sort. So if we look back at the counting sort, there is a good thing, a bad thing. The good thing is we get a really excellent efficiency, big theta of n. The bad thing is the range is highly restricted. This is really bad. So if we always have this condition, then the counting sort may not be very useful in the real world situation. So for that reason, we want to find a better solution. Yeah, because in the real world situation, we need to sort integer arrays without any range limitation. We need to do that. Okay? So when that happens, can we do slightly better than big theta of n log n, right? Yeah. So we may like to do better than this. So next, we need to solve this problem. We try to extend the counting sort to cover, larger range data, integer data. All right. Let us explore the structure of integers another time. Yeah. So we studied the properties, but now let's study the structure. So for the structure, I think we are already familiar with it. So first, let's look at the building block of an integer. So I think it is obvious. Yeah. So let's look at this example. This is a integer. Yeah. Here you can see the building block is digit. We use digits to build this integer. So we need to study the properties of digit and the relationship between digit and integers. Then hope we can have a better solution. So let us study digits. So what is the relationship between digits and integers? Yeah, this question is very simple. So I think everyone here, we know how to write that relationship. Yeah. So let us, review a little bit here. Still, for this decimal integer, how do we view it? Right? So when we view it, although this is an integer, when we consider a typical integer representation, integer, we need to represent it. Then we have many ways to represent it. So for the same integer, so think about this. For the same integer, we have many different ways to represent it. So for example, the most commonly used way, decimal, base 10 representation. Yeah. Another less commonly used, but still used a lot, binary representation. So that's the base 2 representation. Then, less frequently used, but in some very special situation, we may use hexadecimal representation, base 16. Another, very rarely used way to represent octal, base 8 representation. Okay, so here you can see we have different ways to represent the same integer. Yeah. So let's go to the more general case. Yeah. ternary, so base 3 representation. Yeah. We do not have good examples for it. Yeah. But here, when we go to the general, we do not need to use any specific real-world example, but in some special real-world situation, we can easily think in that way. We can easily, get ready to use that way. So let us use our most general expression for it, canary representation. For k greater than 1, canary representation. That is the base k representation. So when you get ready to change different bases for an integer, then you are ready to move to next level solution. Yeah. Integer representation for different bases, based on the observation we did in the previous slide. Now, so let's do that general representation. So digits and the base, there is a explicit relationship to integer. Yeah. So we can write it out easily. Yeah. For example, the base 10, so we write in this way, right? Yeah. For base 2, we write it in this way. Yeah. Then the general base, the base d, so for arbitrary base d number, integer, we can write in this general form. Yeah. The reason we use this general form, because later, when we extend counting sort, we need to get used to this way, using this way to represent our integer data. Depends on the data you get. So what properties? The properties of the data you get. So we may need to choose different bases. Yeah. So we just prepare for that. All right. So in this representation, the condition. So here you can see for the most significant digit, this is the most significant digit. Okay? It cannot be 0. Yeah. Otherwise, we will treat. Otherwise, if it is 0, we don't need this digit, right? So we can save a digit. Yeah. The fewer, the better, right? Yeah. All right. So with this, then let's go to the next step. All right. Number conversion. Yeah. Before we really use it to solve our problem, so let's get ourselves familiar with, the conversion between integers in different bases. So I think you learned this in discrete math, but here let's just get a quick review. First, one direction, the straightforward. Yeah, so we do not need to do anything special. We just do simple calculation. So that is given a base d number, any base d number. So if we use this representation formula, we can easily calculate the, base 10 decimal number directly. Yeah. So for example, so binary to decimal, yeah. So we just plug in this formula, so we get a decimal number. Yeah. Let's look at another one from octal to decimal. Yeah. So the octal given in this way, so we can plug into the formula, so we can get a decimal expression easily. Yeah. So this direction is very easy, straightforward, Yeah, but the other direction, slightly harder, yeah, but not very hard. Yeah. So let's look at the opposite direction. From decimal numbers to base D numbers. Yeah. So convert decimal number to ternary number. So let's look at a simple example. Yeah. Suppose we have a ternary number, so we don't know its expression, but we know its decimal value is 125. So how do we find the digits for its ternary expression? Yeah. So let's use the formula to calculate digit by digit. Yeah. Because when you look at this formula, this representation, so you can find a property. Yeah. So if you look at these terms, they are all multiple of 3. Yeah. But only the first term, if B0 is not 0, it is not multiple of 3. Yeah. Okay? Yeah. So based on this observation, we can find B0 easily. Yeah. So we use a special operator. So that is the, modular operator. Mod. Okay? So let's use this number to mod 3. Because when you mod 3, all the multiple of 3 part gone. Only the remainder part left. This B0 part corresponds to the remainder part. So we can get it out easily. Yeah. So let's just do the mod 3 operation. So you get B0 equals 2. Yeah. After that, all right, so we want to, find the remaining digit one by one. Yeah. So when we go to the next level, we want to eliminate the first term. So how do you eliminate the first term this time? Okay. One simple way to do it, integer division. Because this is the remainder part. Okay? Remainder part. When you do integer division, the remainder part is gone. So you don't want the remainder part. So you do the integer division divided by 3, but only take the integer part. Throw away the fractional part. So then you have the expression of the terms we are interested in. This part, 41. So let's repeat the same method again and again. So this time, 41, we mod 3. We get a B1. That's 2. Then integer division by 3. So B2 plus other terms, 13. Then to find a B2 mod 3 operation another time, B2 equals 1. Then remove the B2 part, integer division another time, B3 plus remaining terms equals 4. Okay? Then we need to find the B3, so 4 mod 3, get 1. Okay? So then integer division, 4 divided by 3, take the integer part, then mod 3, so B4 equals 1. Yeah. So when we get this step, so finally we can write the expression, the ternary expression, from most significant bit, not significant digit to least significant digit in this way. Okay. Yeah. 1, 1, 4, not here, right? So we only look at the modular operation, right? So not the integer division part. So these are the integer division part. Okay? So yeah, modular operation. So 1, 2, 2. Okay, so 1, 1, 1, 2, 2, base 3. Yeah. So that's the, the whole procedure. Yeah. All right. After that, now, so we get ourselves familiar with integers represented in different bases. Next, we are ready to extend the counting sort to a more general sorting algorithm that can handle all integer data without range limitation. That's our goal. Yeah. So we leave that part to part B. So in part B, we will have two topics. So one is the, extension of counting sort. Another interesting problem, so we will look back, revisit one of our old problem. So this time we will get a good solution. String matching problem. So remember, when we study the exhaustive search, we use the brute force method to solve the string matching problem. Now we want to improve it. So in part B, so we will look at that problem another time. All right, so let's stop this part.